A single ant is barely intelligent. It can follow scent trails, carry food, avoid danger, simple behaviors, nothing more. It has no concept of architecture, no understanding of teamwork, no awareness of the colony. Yet when you put 1,000,000 ants together, something extraordinary happens. They build cities, underground chambers, ventilation systems, waste disposal, nurseries, food storage, highways. Complex social hierarchies emerge: division of labor, agriculture, some species farm fungus, warfare, colonies attack rivals with coordinated strategies. The colony behaves like a single superorganism with intelligence far beyond any individual ant. This is emergence. When simple components interact in large numbers, entirely new properties appear, properties that don't exist in the components themselves. Consciousness emerges from neurons, markets emerge from traders, life emerges from molecules. The universe is full of emergence, and understanding it might be the key to understanding everything, from the origin of life to the nature of mind to the structure of reality itself. Emergence is one of the most powerful concepts in science, yet it's often misunderstood. The basic idea is simple. When you combine many simple things, complex behaviors can appear that weren't present in the individual parts. The whole is more than the sum of its parts. But what does more mean? And how does complexity arise from simplicity? These questions touch physics, biology, neuroscience, computer science, philosophy. Everywhere, scientists study systems with many interacting components. Let's start with a simple example. Water. A single water molecule, H2O, is not wet. Wetness is not a property of individual molecules. It's a property that emerges when trillions of molecules interact. Their collective behavior, the way they stick together, flow, and spread, creates the sensation and physics of wetness. You can study a single water molecule in perfect detail and never discover wetness. It only appears at scale. This is weak emergence, higher-level properties that can, in principle, be explained by lower-level interactions, but are effectively unpredictable without observing the system as a whole. Now consider temperature. Temperature is the average kinetic energy of molecules. A single molecule doesn't have temperature. Temperature is a statistical property of many molecules. At the molecular level, there are only individual velocities. At the macroscopic level, temperature emerges. And with temperature come entirely new laws. Thermodynamics. The second law of thermodynamics, entropy increases, is emergent. It doesn't apply to individual molecules, only to large collections. You can reverse the motion of one molecule, but you can't reverse the entropy of a gas in a room. Emergence creates one-way processes, irreversibility, and the arrow of time. Let's go deeper. Phase transitions are emergent phenomena. Water exists as ice, liquid, or vapor, depending on temperature and pressure. The transitions between these phases are sudden and dramatic. At 0 degrees Celsius, ice melts. At 100 degrees Celsius, water boils. These transitions aren't properties of individual molecules. They're collective phenomena arising from interactions among vast numbers of molecules. Near the critical point of a phase transition, the system exhibits scale-invariant behavior, patterns that look the same at every zoom level. This is called criticality, and it's a hallmark of emergence. The brain, ecosystems, and even the universe might operate near critical points, maximizing complexity and adaptability. Complexity science studies these emergent systems. One key insight: you don't need complicated rules to generate complex behavior. Conway's game of life, a simple cellular automaton, demonstrates this. The rules fit on a napkin. Cells on a grid live or die based on their neighbors. Yet from these trivial rules emerge gliders, oscillators, spaceships, even self-replicating structures. Patterns organize, interact, and evolve. No designer, no blueprint, just local rules iterated billions of times. This is algorithmic emergence, and it suggests that the complexity we see in nature, ecosystems, brains, civilizations, might arise from simple underlying rules we haven't fully grasped yet. Ants are a classic example. An individual ant has a tiny brain, maybe 250,000 neurons. Humans have 86 billion. Yet ant colonies solve problems individual ants can't. Finding shortest paths between food and nest, allocating workers to tasks, defending against invaders, regulating temperature and humidity. How? Through stigmergy, indirect communication via the environment. Ants leave pheromone trails. More ants follow stronger trails, reinforcing them. Shorter paths get reinforced faster. The colony optimizes routes without any ant understanding optimization. The intelligence is in the system, not the individual. This is swarm intelligence. Bees, birds, fish, many species use it, and humans have borrowed these principles for algorithms: ant colony optimization, particle swarm optimization. We've learned from emergence to solve our own problems. Flocking birds, schooling fish, and herding animals exhibit emergent coordination. No leader directs the flock. Each bird follows 3 simple rules: stay close to neighbors, match their velocity, avoid collisions. From these local rules, the mesmerizing patterns of murmurations emerge. Thousands of birds moving as one fluid shape, changing direction in milliseconds. It looks choreographed. It's not. It's emergence. The pattern exists at the group level, not in any individual. And it's adaptive. Flocks confuse predators, reduce energy cost, improve foraging. Emergence isn't just beautiful, it's functional. The economy is an emergent system. No central planner decides prices, production, or distribution in market economies. Millions of individuals make local decisions, buy, sell, save, invest, based on their own knowledge and incentives. From these interactions, market prices emerge, encoding information about supply and demand. Adam Smith called this the invisible hand. Friedrich Hayek emphasized that the knowledge needed to run an economy is dispersed, not centralized. No single mind can grasp it. The economy is smarter than any economist. Prices, money, corporations, stock markets, all emergent phenomena. They coordinate human activity on a scale no blueprint could manage. But emergence also creates instability, bubbles, crashes, inequality. The system is too complex to fully control. Now let's talk about life. Life is the ultimate emergent phenomenon. No single molecule is alive. DNA is not alive. It's a molecule. Proteins are not alive. They're machines. Lipids are not alive. They're bubbles. But put them together in the right configuration, and life emerges. Metabolism, replication, evolution, adaptation. None of these exist at the molecular level. They emerge from the interactions of millions of molecules. Life is not a substance or a vital force. It's a process, an emergent process. This is why defining life is so hard. There's no sharp line. Viruses are borderline. They replicate but don't metabolize. Prions are simpler. They just misfold proteins. Self-replicating RNA is even simpler. Life emerges gradually through increasing complexity and organization. There's no magic moment, just emergence. Ecosystems are emergent too. No organism controls the ecosystem. Yet stable patterns emerge: food webs, nutrient cycles, population dynamics. Predator-prey relationships create oscillating populations. The Lotka-Volterra equations describe this. When wolves are removed from an ecosystem, deer populations explode, vegetation is overgrazed, and the ecosystem collapses. Reintroduce wolves, and balance returns. The ecosystem self-regulates, but no part of it is in charge. It's an emergent property of the interactions. Ecologists call this self-organization. It's why rainforests are so resilient and why disturbing them is so dangerous. The complexity is emergent, not engineered. You can't rebuild it from scratch. Consciousness is perhaps the most profound mystery of emergence. Your brain has 86 billion neurons. Each neuron is a cell, biological, mechanistic, unconscious. Yet from their interactions, consciousness emerges. You have subjective experiences. You feel, think, perceive, reflect. How? This is the hard problem of consciousness. Philosophers and neuroscientists have struggled with it for centuries. Some argue consciousness is weakly emergent, fully explainable by neural interactions. We just don't understand the mechanism yet. Others argue it's strongly emergent, something fundamentally new that can't be reduced to neurons. Some even claim consciousness is fundamental, not emergent at all, panpsychism. But the dominant view is that consciousness is emergent. Specific patterns of neural activity, global, workspace, integrated information, predictive processing, give rise to awareness. You are an emergent phenomenon of your brain. Consider integrated information theory, IIT, proposed by Giulio Tononi. IIT defines consciousness as integrated information that's both differentiated and unified. Your brain integrates information from billions of neurons into a single unified experience. A thermostat has minimal integration. A brain has maximal integration. The degree of integration, measured by a quantity called phi, F, determines the level of consciousness. High F, high consciousness. IIT is controversial, but it's an attempt to formalize emergence. If consciousness is emergent, maybe we can measure and predict it. Language is emergent. No individual invented language. It evolved through countless interactions among speakers. Grammar, syntax, semantics, all emergent. Noam Chomsky argued for a universal grammar hardwired in the brain, but many linguists now favor emergentist approaches. Language arises from communication needs, cognitive constraints, and cultural transmission. Creole languages, born when speakers of different languages create a new common language, emerge spontaneously with complex grammar within one generation. Children create grammar even when exposed only to pidgin, simplified language without grammar. Language is so natural, so emergent, that children generate it from minimal input. This suggests the human brain is an emergence engine, extracting patterns and generating structure. Cities are emergent. No one designs a city in full detail. Mayors and planners make decisions, but the city's character, its culture, economy, traffic patterns, social networks, emerges from millions of individuals interacting. Geoffrey West and colleagues discovered scaling laws in cities. When a city doubles in size, infrastructure, roads, pipes, increases by 85%, but economic output and innovation increase by 115%. Cities become more than proportionally productive as they grow. This is superlinear scaling, an emergent property. Why? Because density increases interactions. More people, more meetings, ideas, collaborations. Emergence accelerates. But crime and disease also scale superlinearly. Emergence amplifies both good and bad. The internet is emergent. No one controls it. DARPA created ARPANET, but the internet grew chaotically. Billions of users, trillions of links, emergent phenomena everywhere. Viral memes, social movements, collective intelligence, Wikipedia, distributed computing, black markets, echo chambers. The structure of the web follows a power law. Most sites have few links. A few, Google, Facebook, have billions. This is a scale-free network, emergent from preferential attachment, new nodes linked to popular nodes. The internet is smarter than any individual website, but also more dangerous. Misinformation spreads emergently. Algorithms create filter bubbles emergently. We designed the components, but the system behavior surprises us. That's emergence. Artificial intelligence is starting to exhibit emergence. Large language models, trained on vast text datasets, develop abilities not explicitly programmed. GPT-3 and GPT-4 can reason, translate, write code, even pass exams. These abilities emerge from scale and training. Researchers didn't program logic or translation rules. They just trained the model on data. Capabilities emerged. This suggests that intelligence itself might be emergent. Scale up neurons, or parameters, add learning rules, and intelligence appears. This has profound implications. If intelligence is emergent, we might create superintelligent AI by scaling existing systems. But we might not understand or control it because emergence is unpredictable. Now let's consider strong versus weak emergence. Weak emergence, higher-level properties are surprising and hard to predict, but in principle fully reducible to lower-level laws. Temperature, wetness, flocking, all weakly emergent. Strong emergence, higher-level properties are not reducible, even in principle. They exert downward causation, influencing the lower level. Consciousness might be strongly emergent if it can't be fully explained by neurons. Some philosophers argue strong emergence violates physics. If higher levels cause things not explainable by lower levels, where does the causal power come from? Others argue it's compatible with physics if emergence is about patterns and information, not new physical forces. Downward causation is controversial, but important. Does the mind cause neural activity, or do neurons cause mind? In weak emergence, it's all bottom-up. Neurons cause mind, and mind causes neurons is just shorthand for neural patterns cause other neural patterns. In strong emergence, mind genuinely influences neurons in ways not reducible to neural mechanics. Most scientists favor weak emergence, but the debate continues. Emergence also appears in physics. Superconductivity is emergent. At low temperatures, electrons in certain materials form Cooper pairs and flow without resistance. This behavior doesn't exist in individual electrons. It emerges from quantum interactions among many electrons. Superfluidity, magnetism, and even spacetime itself might be emergent. Some quantum gravity theories suggest spacetime is not fundamental, but emerges from quantum entanglement. If true, space and time, our most basic concepts, are emergent properties of a deeper quantum reality. This would be the ultimate emergence. The universe itself might be emergent. In Lee Smolin's cosmological natural selection, universes reproduce through black holes, and physical constants evolve. In Max Tegmark's mathematical universe, physical reality emerges from abstract mathematical structures. In digital physics, the universe emerges from computation, cellular automata, or quantum bits. These are speculative, but they take emergence seriously at the deepest level. Maybe existence itself is emergent. Maybe nothingness is unstable, and somethingness emerges spontaneously. Emergence all the way down. What does emergence teach us? First, reductionism has limits. You can't understand everything by breaking it into parts. Sometimes the whole has properties the parts don't. Second, complexity doesn't require complexity. Simple rules can generate rich behavior. Third, the universe is creative. It generates novelty, new structures, new behaviors, new levels of organization. Fourth, control is an illusion. Emergent systems resist top-down control because their behavior arises from bottom-up interactions. You can nudge them, but you can't dictate outcomes. Practically, emergence matters everywhere. In medicine, diseases emerge from complex interactions: genetic, environmental, microbial. Treating one component often fails because the system adapts emergently. In engineering, emergent failures, traffic jams, power grid cascades, financial crashes, surprise us because they arise from interactions, not individual parts. In AI safety, emergent capabilities in large models pose risks because we can't predict what they'll learn. In climate science, tipping points are emergent phenomena, sudden shifts when the system crosses a threshold. Philosophically, emergence challenges our sense of understanding. We like to explain things by reducing them to simpler parts. Emergence says, sometimes you can't. You have to study the system as a whole. This doesn't mean mysticism or vitalism. It's not magic. It's just that nature operates at multiple levels, and each level has its own laws. The laws of chemistry aren't just applied physics. They're emergent from physics, but expressed in new language: molecules, reactions, bonds. Biology isn't just applied chemistry. It's emergent: evolution, ecosystems, behavior. Psychology isn't just applied neuroscience. It's emergent: personality, culture, meaning. Each level is real. Each has its own explanatory power. So when you look at an ant colony, a flock of birds, a city, a brain, or the universe, remember, you're seeing emergence. The magic isn't in the parts. It's in the interactions. The dance between components creates something new, and that newness is what makes reality interesting. Without emergence, the universe would be boring, just particles bouncing forever. With emergence, we get stars, life, minds, love, art, science. Emergence is the universe's way of creating itself. Simple rules, iterated endlessly, building layer upon layer of complexity, until atoms become aware, until the universe opens its eyes and asks, how did I come to be? And the answer is emergence, one interaction at a time.